Welcome everyone. Uh, Myself Himanshu Thapliyal. I'm a professor in the Department of Electrical and Computer Engineering at the University of Kentucky. Today I will be giving my talk on energy recovery computing for low energy and secure IoT devices. So this is the general overview of Internet of Things. As you can see that there is a growing interest in the Internet of Things, as can be evident from this graph. And you can say around 2020, we're expecting around 250.1 billion IoT devices. IoT has a growth in everywhere, for example, in the retail section, in the communication section, medical, and everywhere. And you can think in this case right now, it is application even the smart home environment, in the wearable devices. So IoT is everywhere, right? In the industrial application, everywhere. Now, whenever you are looking for IoT devices, the interesting thing is that these IoT devices usually work at low frequencies. However, you have some design challenges. The design challenges are that you need to have the system that are energy efficient, and you want to also have them secure. These are the design challenges, and the reason is that usually most of these IoT devices are typically battery operated, and so you want to have the system which is energy efficient, right? However, these devices are also vulnerable to the hardware and the malware attacks, right? And they're also susceptible to the side channel attacks. One of the major attack is the power analysis based attack, which we'll be discussing today. Moreover, nowadays, because many of the foundries are outside US, so these devices could also be subjected to like the IC piracy, counterfeiting, and the hardware Trojan. So, so one such example is, which we'll discuss today, is the differential and correlation power analysis based side channel attack. So the idea is that suppose you have a smart card and you can evaluate some sort of the power consumption in some sort of system, and through which you can decipher your keys, that is making your that is used for encrypting your data, right? So one such example that you can do is that you can, this is your input data, this is the device under attack. Another thing that you can do is that you can also create an abstract model. And here, this is the input and this is the key guesses that you're trying to do. And then you can perform some sort of a statistical analysis. And based on that, you can correlate, say example, your expected key with the actual key, and based on that you can decipher your key, right? So you can use power profiling for doing that. Now, so in the existing literature, people have explored several types of countermeasure against this one. And this is one illustrative example. The countermeasures can be in algorithm level, or it can be also at the circuit design level. And this is what is of interest to us at the circuit level. Here you can think in this case, even they can also be at the full custom implementation, or they can also be type of standard cell-based designs. Now, if you look into some of the existing countermeasures that people have explored, here you can see here, this ER column represent the adiabatic logic based style, that the energy recovery based solutions. Now, but the interesting thing you can think in this case is that all the existing solutions provide some level of DPA resilience, but at the cost of increase in power consumption. But the adiabatic logic is the only solutions which provide you the resilience against this power analysis based side channel attack, while further reducing the power consumption. So that is the very, very important factors that make this adiabatic logic very, very interesting to explore. Now, one thing that I like to emphasize is that this result that is being shown in the table 2, they are the actual silicon based result. The chips have been fabricated, and the results are fabricated, and the results are evaluated on the actual silicon hardware. Now, today in this talk, we will show that how this energy recovery logic, or the adiabatic logic, can be used for developing this low power and DPA resistant circuits. We'll explore that how this emerging devices such as FinFET or tunnel FET can be used with adiabatic logic styles. We will show that how this adiabatic logic based circuits can be used for designing the physically unclonable functions. how this adiabatic logic styles can be used for hardware Trojan detection, and what are the challenges and the possible solution to make adiabatic logic styles as a attractive choice for the industry adoption. And this all the research is being supported by the NSF Career Award. So this is the general overview of this energy recovery logic or the adiabatic logic. Usually you have the constant VDD in the classical CMOS, but in adiabatic logic styles, you have this constant VDD replaced by a power clock. So you think in this case, the clock, so here the clock goes more or less like this. So whenever you can think in this way, the clock is going right, this is being represented here. So the energy is being supplied to you, some of your output nodes. And then when the clocks fall down, what you do is that instead of dissipating the energy to the ground, you recycle the energy back to your clock source. So that's why you can say you are trying to recover the energy. That's why these circuits are you can say consume less energy. Moreover, you can think in this way because you, instead of having the constant VDD, here you have the time ramp that is being illustrated here. So the dissipation is also you can say is proportional to this time ramp that is given by T. So the higher the T, this means this circuit can consume very, very less energy. So that's why these circuits are especially suitable for low frequency IoT applications. Now, this is one illustrative example of the current trace of the inverter. If you look into the CMOS-based inverter here, you see that based on the input transitions, you can see the different types of peak in the current, right? Here there is a very small peak, here there is almost a straight line, then it suddenly goes up. So for the attacker, it is very easy to attack a classical CMOS-based circuit because this current profile is dependent on the input transitions. Now, if you look into this, so people try to explore the CMOS-based dual rail solutions. This is one illustrative example. However, you can say here the power profile has become uniform, but the peak current has become very high. That's why these circuits, which is the classical CMOS, can provide security, but at the cost of increase in power consumption. Now, this is one of the solutions that we have proposed. This is the adiabatic logic based styles for providing the low energy and secure solutions. Here you see that the power profile is uniform. It is independent of the input transition that is happening. Moreover, the peak current is very, very less. So by suppressing the peak current and making the uniform power profile, we can make our circuit resilience against these power analysis based side channel attacks. So this is the general overview of the adiabatic logic. You can see in this case, if you have the vulnerabilities, the energy consumption, so by using this adiabatic logic solutions, you can develop this secure as well as the low energy solutions that can have several applications either in the smart home, smart healthcare, wearable, and the IoT devices. That is a great and you can say the novel application for the adiabatic logic styles. Now, one such example of this adiabatic logic family is the symmetric pass gate adiabatic logic. Here you can think in this case that generally this portion will help you to recover the energy, and this is your logic block, okay? And so this is general overview that you can see. This is the one of the adiabatic logic families that we have developed. Now, what we think in this case is that this is an example of an XOR gate. What you can observe here that the power profile is uniform, as can be evident here, right? Now, what we did is that we use this adiabatic logic style and try to implement one of the key component of the AES cryptographic algorithm, and we observed that the S box is consume the 75% of the power consumption of the AES cryptographic hardware. So what we did now is we try to implement this S-box circuit using this proposed adiabatic logic style. And this is, if you implement in the classical CMOS, you think in this case the energy dissipation is around 11.45 picojoule. But if you use our approach, the adiabatic logic style, the power consumption is only 0.825 picojoule. So adiabatic logic has almost, you can say, 14 times less energy consumption compared to the classical CMOS. Now what we can do, we try to also see if we can use this adiabatic logic style with some of the devices as FinFET and TunnelFET. And the idea is that by using this adiabatic logic technique, we can save this dynamic power, we can have a dynamic power reduction. And by using devices such as FinFET and tunnel FET, we can achieve the leakage power reduction. So that was the idea. And this is one illustrative example we implement with this adiabatic logic in tunnel FET. And then you can see that the power profile is uniform irrespective of the input transition. This is an example of the XOR gate. Moreover, the peak current is also very small, right? So that is the major feature. So by suppressing the peak current, we can make the circuit more secure. So now what we did, we tried to implement a present AT algorithm, and I will show you some case studies result based on that. So this is the present AT algorithm at 12.5 megahertz because we are targeting IoT applications. So what we can think in this case is this is the classical CMOS, this is the adiabatic CMOS, this is the adiabatic FinFET, this is the adiabatic tunnel FET. So now you see that, of course, this adiabatic CMOS has low power than the conventional CMOS. Then this FinFET-based adiabatic logic has low power compared to the adiabatic CMOS. Similarly, this tunnel FET-based adiabatic logic style has low power compared to the FinFET-based logic style. So what we can see that from this one, that merging adiabatic logic style with these emerging devices which can have low leakage can result in very, very low energy and secure solutions. So now what we did, we tried to implement this and try to perform a DPA attack on the present AT. So you can see that here in the CMOS, the key is coming out very quickly, so people can decipher the key. But in case of adiabatic logic styles, you can say that the correlation coefficient is very, very small. Here you can say the correlation coefficient is 1, 0.8, but here is 0.0001. So the correlation coefficient is very, very small. So even after 10 to power 4 traces, we were not able to decipher the right key. So that shows that this adiabatic logic style is a very, very good solution for developing this DPA resistant hardware. Now, we will show another application of these adiabatic logic styles for developing this hardware security primitive. So one interesting primitive is the physically unclonable function. So physical unclonable function can be more or less considered as a silicon fingerprint. So you can think in this way, each one of have our own DNA, and the DNA is unique. Similarly, because of this manufacturing variations, what is there is that each chip will behave in a unique way. So if you pass a unique challenge to two separate chips, we call it puff right now, these physical unclonable functions, their behavior should not match. Okay. So what we did is that we try to use this adiabatic logic idea, and here we replace this. You can say this is the power clock, and this is the cross-coupled latch, right? So what we did, because of the process manufacturing variations, there will be a threshold mismatch, and accordingly, this R and R bar can settle to either to 1 or 0 depending on the threshold mismatch. So we have used this idea to develop this physically unclonable function. So more details can be found in this paper. But the interesting idea that I want to illustrate to you guys that at 45 nanometer, this is the result we tested. The circuit that we use for based on this adiabatic logic style, it has very, very high reliability. And also, if you see from the compared to the existing approaches, the energy per bit is also very small. See here, you can think in this case, this other circuit is there, but the reliability is very less of this existing circuit. Our circuit, that is adiabatic, has high reliability. Also, the energy is very small. So that is a very good another application of adiabatic logic. Now, another thing that you can think in this case is that this adiabatic logic can also be used for hardware Trojan detection. So what is a hardware Trojan? So these are the malicious circuits that can be inserted in your actual hardware to perform the faulty operations. So people have some malicious intent. So they are more like the hardware malware, you can think in this case. So if you have an adiabatic logic style that can perform the uniform power consumption. So if you insert this hardware Trojan like here, so whenever you compute, you can think in this case, usually if there is no Trojan, your power profile will be like this. But whenever there is a Trojan is inserted in an adiabatic logic circuit, the power profile becomes slightly, you can see the peaks coming out. So by capturing these peaks, we can easily identify the hardware Trojan. So you think in this case, previously we were trying to make the uniform power consumption for developing the DPA resistance. Now we can use the uniform power consumption in the adiabatic logic circuit for detecting the Trojan. So that is another application of this adiabatic logic for security. Now, the challenge is that how can we make this adiabatic logic as a popular design style for the industry? So there are some major challenges, what we think in this case. First of all, there is a amount of time and effort required to design this adiabatic circuit is very high, because most of them have the are need to be designed as a customized hardware. So it's a lot of work. You have to design the custom layout and everything. So it's a lot of manual work. So moreover, for example, the designer has to learn the specialized skills that is based on adiabatic logic style to learn that. So that is slightly a different logic style compared to CMOS. So that is also a bottleneck. So how can we help the designer? So in our opinion, if you see this case, this is the overall idea of this adiabatic logic circuit. You have this power clock generator. This is the logic circuits. So here, let's address this one. So we think that the best solution to make it popular is to develop some sort of standard cell libraries of these adiabatic logic circuits, and so that we can use some sort of semi-automatic tools such as existing EDA tools, so that it becomes more, so that adiabatic logic style becomes more popular. Now, another interesting thing we can think in this case here is this is the classical, you can think in this way, classical EDA flow. Now here, this clock tree synthesis in your case will be replaced by this power clock routing and power clock synthesis, right? Because you have the instead of the actual clock tree, you have the power clock that need to be routed. So in our opinion, we think that the best possible solution to achieve this is to use this two-phase adiabatic logic. So the idea is that if you have more phases, you have more clocks to route. So that becomes very difficult. This is one illustrative example. In which the first figure shows the four phase. So you have to route four phase. But if you propose two phase, then you have to route only two of these phases. So which is very easy, because now you're writing more or less routing like your VDD and the ground. So one of them is representing the VPC1, another is representing VPC2. So it is very easy. So it will lead to reduced interconnection, and it is much easy for the designer to lay out the chip. Now, what we did, we proposed this two-phase adiabatic logic that is secure. More details can be found in this paper. It received the best paper award recently in the IEEE 6th World Forum on Internet of Things. So this is the V clock, and this is a V clock bar. You can say now it is sinusoidal. So it is only two phase. So now what we did is that we tried to develop a two-phase power clock generator, and we developed this present 80, we integrated it together. Now, if you see, this is some of the preliminary result that we observe. You see at around very, very low frequency here, the adiabatic logic style, even integrated with the power clock generator, has around 77% low energy consumption compared to the standard CMOS. Of course, as the frequency increases, the power consumptions is around 21% right now. But this is, you can think in this case, if we try to develop this power clock generator in a more and more efficient way, then of course this number is going to be high. So that is one of the research that we are trying to explore. So in summary, what we can observe that adiabatic logic style is very promising solutions to develop the low power and the secure hardware, but we need to do some more research to make it easily accessible to the VLSI designer. And what we think in this case, we need to do some research in developing some sort of standard cell libraries. We need to look for possible solutions. And one of the possible solutions that I right now mentioned is the use of two-phase adiabatic logic. That is a very, very unique style, and it is also promising, and all the standard tools can be used to easily for the custom layout and all those things, right? So, and even for the automatic layouts. So with that, I like to conclude my talk that AR computing is a promising candidate to implement low power hardware security solutions, and which have stringent constraints on the power consumption. So with that, I like to conclude my talk and thank you very much.